Hello everyone and welcome to today's webinar. Today's webinar is titled Automatic Ergonomics Whole Body Motion Analysis and Physical Human-Robot Interaction. My name is Christopher Iversen and I work here at Anybody Technology. Today I will be the host of this webinar and I'll be joined by my colleague Bjørn Keller Ingelund, who is one of our research and development engineers here at Anybody. Bjørn will join us during the Q&A session in the end and help us out with answering your questions. In today's webcast, we have an external speaker who is postdoc Valdis Gomes from the University of Paris-Saclay. Valdis' research area is human exoskeleton interaction, and in today's webcast, he will share insights in his approach to evaluate the human motion with respect to ergonomics and much more. Valdis is going to give his presentation in a minute or so. But just before we start, I will give you a general introduction and overview of the Anybody modeling system, for those of you who is unfamiliar with the software or musculoskeletal modeling and simulations in general. So let's begin with having a look at what the Anybody modeling system actually is. Well, the Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data as kinematics and forces, and it calculates internal body loads as joint moments, joint reaction forces, and muscle forces. And down here in the bottom of the screen, you can see a screenshot from the actual software, which can give you an idea of how the system looks. At the moment, Anybody is used in a wide variety of areas and applications, and a few examples of this is movement analysis, product optimization design, the field of sports optimization, orthopedics and rehabilitation, and assistive devices as exoskeletons. The typical workflow in Anybody could look something like this. So you provide the recorded motion data as input, and then you can use the body models which you or others have built. And then you can provide some kind of environment, which could be a special type of equipment, for example, an exoskeleton. You can then use Anybody to combine these things, solve the muscle recruitment, and run the inverse dynamic simulations. This basically means that we go from motion to calculate the internal body loads and the interaction with the environment in some cases. And it gives us a simulations that look something like this. You can then output the results and use it for some kind of post-processing with for example, a finite element tool. But many users also choose to complete this loop by doing some kind of design optimization and then run this cycle multiple times. And this actually brings me to the end of the introduction, and I will hand over the word and present the role to Valdis instead.
Good afternoon, everybody. Thank you all for your presence here in this webinar. Today, my talk will be basically a broad overview of my work during my PhD thesis in ergonomics that was financed by the European project ANDI. It was also supervised by Dr. Jean-Baptiste Moret and Dr. Serena Ivaldi, as well as co-supervised by Dr. Pauline Maurice. So I will start from a wider context of robotics, and then I will present some of the scientific problems behind this talk per se. And then I'll move on to more technical details of the studies and the solutions developed around those problems, namely automatic ergonomics evaluations, human motion generation, and then I'll very briefly talk about a couple of studies that involved human motor behavior and human-robot interaction. So let's move on now to the introduction. In the past, robots were always assumed to be part of self-contained automated cells with a very good task execution precision and repeatability. However, with a limited ability to be compliant, along with their high power, they were commonly restricted to caged or fenced workspaces. In an attempt to remove the workspace restriction, many researchers started looking for ways on how to make robots safer to the human presence. In that context, different kinds of robots started to emerge, with compliant joints, special mechanics designs, and other features that were specially conceived to increase the safety of the humans around them. In the future, we would like to have robots that are more and more physically interacting with humans under collaboration interaction behaviors, in which the main goal now would be to execute the task while harnessing both the robot's power capabilities and the cognitive skills of the human. Therefore, over the years, we have seen this ever-increasing complexity in human-robot interactions. And as we can see in the figure, the more complex the interaction between them is, the more human-aware the robot now has to be. Robots that are not ready for interaction are completely agnostic of human interaction and require only a fence to ensure the human safety. But on the other side of the spectrum, if the human and the robot are working as a team in direct contact, the robot now needs to know the human status, which is something that is not trivial, possibly with sensors equipped on the human, such as for human localization in space or to measure the body posture. Only then the robot will be able to modulate its behavior to ensure not only the task execution, but also the safety of the task. In the figure on the top, in the circle on the top right, there is an example of an exoskeleton robot that is in direct contact with a human worker. In this application, the robot tries to alleviate the efforts of the worker while he or she lifts heavy objects over the course of a workday. It is important to note that in this application, it was designed to improve the ergonomy of the task. As a matter of fact, poor ergonomics conditions is a major issue in industry. For instance, overexertion of forces, awkward body postures, and excessive motion repetition are all known causes of work-related musculoskeletal disorders, WMSDs, both in the short and in the long term. And those represent a large cost not only to the workers, but also to companies in general. So during my thesis work, the main goal was to improve on human-robot collaboration to specifically improve ergonomic conditions. In sum, the question here is, how should we design a human-robot collaboration to favor ergonomics? And then the overall goal becomes to provide tools to make ergonomics interventions using robots, including exoskeletons as a medium for that. The research presented here in this talk was funded by the European project ENDI. In the ENDI project, it foresaw robots that sense relevant data from their human partners in order to predict and anticipate the human. This way, the robot would be better equipped to act and react to the human. In this context, because our main goal was to improve ergonomics, the first thing that we had to consider was then to measure the ergonomic status of the human in real time. If the robot is aware of the ergonomic status, now it may be capable of driving the human towards more ergonomic body postures. But to do this, the robot also needs to be aware of what does it mean to interact with the human. It needs an interaction behavior model, which is out of the main scope of this talk, but that we will briefly talk about it in the end of it. Now, we're going to take a closer look into the ergonomics status measurement, or estimation. On the top right of this slide, we can see two very different strategies of motion, to lift a heavy object from the ground. In this example in particular, the left motion requires more forces, more torques at the lumbar back, at the lower part of the back of the subject, than the motion on the right. But the important question here is, how do we generalize this process? How do we know generically which strategy of motion is better, and which ergonomics criteria do we use for that? Well, there are some classic evaluation tools that are commonly used in industry for this matter. such as Rula, Reba, AWS, and some other tools. However, the main caveat of these tools is that they're manually filled worksheets by experts. Those experts, evaluators, have to observe the task and visually identify the body posture angles, for instance. Different evaluators could then have very different evaluations. If the evaluation is based on video material, then even the video quality could bias the results. Also, if the evaluation needs to be redone, it will be subject to the availability of an expert. If the expert is not available, it will not be possible to do the re-evaluation. Lots of the problems associated, so most of those problems can be avoided if now these tools are evaluated automatically. Even though the worksheets were not designed for this, another aspect of the motion that is not properly evaluated by them is poor dynamics evaluation. In the lifting example, the subject is lifting a 10-kilogram weight with a proper posture and form. But what if instead of 10 kilograms, he tried lifting 20? Would it still be okay? Well, most worksheets would actually penalize both situations equally, even though the efforts in the body will be different for the two cases. Furthermore, people also have very different power capabilities. The same 10 kilograms that was fine for this subject may in fact be dangerous for another one. For this reason, fine dynamics evaluations of the motion is actually very relevant for the ergonomic status evaluation as well. If we're able to evaluate both kinematics and dynamics aspects of a motion for different kinds of people, we should also be able to generate optimal ergonomic motions for those people. And then, such reference motion could finally be used as a reference for our robot controller. In the remainder of this presentation, I'll describe the tools that solve some of the issues exposed in this introduction. Let's move on to the automatic ergonomics evaluation. Well, one of the very most important things for automatic evaluation is to have a digital human model, a DHM. Digital human models are mostly used to simulate the human motion under a variety of situations, such as with wide ranges of work environments or setups, as well as performing diverse motions. Using digital models to simulate motions make it possible to evaluate the human motion without the risk to harm actual human subjects. Some models, some digital human models, can even be used to obtain very complex analysis, such as estimating efforts at the musculoskeletal level, like the antibody modeling system, for instance. However, at a high computational cost. Now, let me show you an example application that used such human model systems. Recently, within the Indy project, several research teams realized an ergonomics assessment of the commercially available BackX shoulder exoskeleton that is manufactured by the company Ottobock. They developed an experimental setup where the subject had to perform a simulated overhead drilling task while wearing the exoskeleton from Ottobock. From this experiment, they were also able to use their data to simulate the human motion alongside an exoskeleton model using the antibody modeling system. The simulation took as input the human kinematics as well as data from ground force plates and angle torque measures from the exoskeleton. It was finally able to output valuable muscle activity and joint reaction forces, all those which are measures that are very valuable, as they are a kind of estimation or even measurement that is very hard to obtain directly. However, in the context of my thesis, that aimed not only to evaluate and assess the capabilities of an exoskeleton, but also to generate optimal ergonomic motion, this kind of detailed simulation was actually very costly time-wise. In order to generate optimal motions, we actually needed a human model simulation that was also very computationally light, so as to be repeated several times for different motions. A model with such characteristics is used by the Xsense MVN system, with interconnected rigid body segments that can also be scalable according to the user's body morphology. However, this model only represents the geometry of those segments. Therefore, using it directly, we cannot use it to evaluate motion dynamics directly. To be able to do that, to be able to evaluate the motion dynamics, we designed our own human model with not only scalable geometry, but also scalable inertia elements for the body segments. Now, to track the desired motion of our DHM in a physics-based engine and perform dynamics evaluations, the model also needs to be controlled. In order to do this, we use the technique that is very used in humanoid robotics. The whole body motion of the DHM is actually controlled using a quadratic program controller. The program receives reference inputs regarding Cartesian and postural trajectories for different tasks for the entire whole body. Then it calculates the joint velocities that minimize the tracking error of those tasks. In addition, in this quadratic program, this QP controller, the hierarchy of the defined tasks are determined using a stack of tasks framework, the OpenSOT framework that I cite in the bottom of the slide. So in this framework, tasks on lower priority levels are solved within the new space of tasks on higher priority levels. Then tasks on the same levels have their hierarchy solved by real valued weights, which are highlighted in the slide and within the orange circles. As for the ergonomics evaluations per se, several scores can be calculated using our DHM simulation, including a continuous version of the classic ruler score, an index of whole body effort for the whole body torques, and some other local measurements. In our case, we chose to verify the torques at the shoulder and at the lumbar joints of our DHM. As well, we also looked at the back flexion angle in our DHM. The key point from using all of those several ergonomics scores is actually that each one of them assess different aspects of the movement, and they can be used to evaluate the different musculoskeletal disorders risk factors of each one. So in the next slide, I'm going to show you an example of a usage case where we used this DHM simulation. So we have this interesting application that was executed during the ExoTurn project in partnership with the INRIA Nancy in France and with the University Hospital of Nancy. The activity that you see in the video is commonly performed on patients by health professionals in hospitals because it's basically a treatment for patients with acute respiratory diseases. With this ongoing COVID-19 crisis, it has been executed at very high rates in hospital ICUs throughout the world. Then we identified that in this activity, it is basically very strenuous for the health workers, the health professionals. And then we proposed the usage of exoskeletons to alleviate the force and torque efforts at the lumbar back of the workers. In this context, we designed a preliminary experiment to capture the motion of the health professionals while using some commercial passive exoskeletons, as well as to gather qualitative feedback from them. In this preliminary experiment, we acquired qualitative feedback from 4 commercial back supporting exoskeletons: the BackX, the CrayX, the Corfor, and the Laevo exoskeleton. The Corfor exoskeleton was easy to deploy, but in the health professionals, the health workers, nurses and doctors, physicians, did not perceive any major difference while using them. On the other hand, both the CrayX and the BackX were reportedly too cumbersome to use while executing the prone positioning task. And finally, we had the Laevo exoskeleton. That was the one that checked all required boxes for deployment in the hospital, while also supporting the back effectively during the task. With this in mind, we propose to use our digital human model to evaluate the motions of the human with and without the Laevo exoskeleton. Here, the motion is captured using the XSense system. Some Cartesian trajectories are then retargeted from the XSense model to our human model simulation using the QP controller that I previously mentioned, and then its own associated stack of tasks. Then, for each motion, the torques at the model's joints are estimated. With this torque measurement, these estimations, we can estimate the human torque efforts at the lumbar back, as long as we can also estimate the exoskeleton calibration curve. For the used exoskeleton in particular, we based its torque calibration curve on a previous study from the literature. As a result, we estimated a reduction in the median lower back torques of the human models of about 11 to 13% during supine to prone and prone to supine movements. Not only the torque reduction, but we also observed a similar range of motion with and without the Laevo exoskeleton. That's basically the plots on the bottom part of the slide. This plot is it's not meant to check for the difference in the medians, but actually just to verify that there was no difference in the range of motion for the different exoskeletons. Therefore, the quantitative analysis suggests that the exoskeletons alleviated the efforts while not interfering in the task execution. And then the other thing I have to say here is that these results should actually be taken with a grain of salt, as the exoskeleton itself was not added to the physical simulation in this study, and its weight could have had, as a matter of fact, a significant impact in the result. Well, now that we're able to automatically evaluate kinematics and dynamics aspects of the whole body motion, we can use these tools to propose methods to generate optimal whole body motions. In our proposed methods, first, we capture the initial movement from a human demonstrator, and we encode the whole body movement into a single vector W. Then, the movement is executed within the digital human simulation. And finally, the motion is optimized with respect to the ergonomics evaluations presented previously. Regarding the encoding of the whole body motion, there are many possible ways to encode a trajectory. Here, we chose to use an approach that is based on probabilistic movement primitives, also known as ProMPs, which are basically stochastic representations of a movement trajectory. They were chosen because they can be trained from an entire set of demonstrations, hopefully obtaining a better representation of the motion. In addition, mean ProMP trajectories can be represented by a low number of parameters, as they are a weighted sum of radial basis functions. On the top right of the slide, you can see an example where the radial basis functions that compose the mean trajectory of the plots on the bottom right. So from a whole body movement, we select Cartesian trajectories, which are sufficient to describe the entire movement. In the example on the right, we chose to learn ProMPs from the hands, center of mass, and pelvis trajectories. All weight vectors from each one of those trajectories that were learned for ProMPs are then stacked into a single vector W. This vector W now defines the motion that is going to be evaluated in the human model simulation and is therefore our optimization variable. Now, let's take a look into an example for our optimization methods. In this example, we see a work activity where a human subject lifts a box from the ground. On the right, the DHM is replaying the lifting movement from the left. Note that the original movement was intentionally a non-ergonomic movement, so that there would be a visible room for improvement using our optimization methods. Here, as for the control of our DHM, the stack of tasks include higher priority tasks for the feet to ensure double support of the model, a task for the center of mass for the model movement and balance, and lower priority tasks for the hands, pelvis, and postural tasks. The trajectories we chose to optimize are highlighted in red in the slide, namely for the center of mass planar projection and the pelvis vertical trajectory. So first, we optimized each ergonomics score separately using single objective optimizers for our black box optimization problem with nonlinear constraints. In this video on the slide, you can see a comparison between the initial motion and the motion optimized with respect to the Rula continuous score. This single objective optimization was done for all of the other scores that I previously mentioned. As expected for all of them, all of the optimal solutions had generally the strategy of increasing the knee flexion and decreasing the back flexion of the model. However, at a closer inspection, they have indeed different outcomes between them. In this slide, we can see a polar or a spider chart where each color represents the scores of a whole body movement with respect to the initial motion. In particular, the initial motion here is represented with the red color. From here, we observe that some optimal solutions actually highly increase the torques at the shoulder level. This is actually a strong indication that optimizing for only one single objective could transfer the risk of a musculoskeletal disorder from one region of the body to another body region. In particular, we also identified that the optimal solution with respect to the lumbar back torques is actually detrimental to the shoulder torques and vice versa. So there is a compromise in there. To handle this compromise properly, we need to take a different approach from single objective optimization. We need to take a multiple objective approach. So multiple objective optimization handles multiple conflicting objectives, such as the example functions f1 and f2 that are depicted on the top right of the slide. To optimize them simultaneously, a common approach is to aggregate the objectives using a weighted sum, such as the one given by the aggregated function on the slide g, and its weights a1 and a2. And then optimize the aggregated functions using single objective optimization as usual. However simple, this approach has indeed a major drawback when we're talking about ergonomics. The weights that aggregate the functions here, they implicitly encode solution preferences. If this is an ergonomics motion problem like horse, and our ergonomics expert chooses A1 to be much higher than A2, then the solution will favor the minimization of F1. If the expert decides posteriorly that the choice was not satisfactory, then the weights have to be chosen again, and consequently, the optimization will have to be run again as well. In our case, a single objective optimization takes approximately 15 hours. So this may be very costly time-wise already. It's better not to do that every time that we need to change preferences. Alternatively, we can use a more general approach, a Pareto-based multiple objective approach. In contrast with the aggregated function approach, this one outputs not only one solution, but an entire set of non-dominated solutions that encode many possible solution preferences, a Pareto front. Therefore, now if the expert changes his mind about which objective to favor when generating the optimal motion, then the optimization process does not need to be run once again. Let's now see how this was applied to the box lifting example. We followed by using a classic multiple objective optimizer with the ergonomics scores for both the torques at the shoulder and at the lumbar back segments that we verified that there was a compromise for. On the bottom right of the slide, there is a selected motion from our resulting Pareto front that is indicated in the plot right here in orange from the table to the Pareto front in the plot. We can note here that the selected solution in orange, that we've seen in the slide previously, from the Pareto front, is indeed safer from an ergonomics point of view than the single objective solutions for each one of the scores, for each one of the single objective optimization solutions. In sum, those were methods for whole body motion optimization, where we can specify the activity requirements and the worker's body morphology. The optimal ergonomic motions are obtained using single and multiple objective optimizers. In particular, we showed that multiple objective optimization can produce motions that simultaneously minimize several ergonomics scores. Those ergonomic trajectories, whole body trajectories, could now be used as references for robot controllers. However, as I mentioned before in the introduction, it is not yet clear how humans act during physical interactions. So here I'm advocating for robots that they also need to be aware of the interaction motor behaviors done by humans. One possible approach that was taken during my PhD was to first study the human motor behavior during a joint task and then try to emulate it posteriorly with a robot partner. In particular, we developed this task that you can see in the video, where a human dyad, needed to execute a co-manipulation task. In the task, the agents had to remove a pipe from a tube while not touching the tube's walls, move the pipe around a cylindrical obstacle, and finally inserting the pipe into a second tube, again without touching the tube's walls. As you can see, this task needs some high level of accuracy at executing it successfully. And on top of that, we designed the experiment to be executed during different coordination strategies for the human-human diet. In two conditions, one agent was the leader, while one was the follower, and vice versa. And in the third condition, there was no pre-assigned leadership. One of the main questions of this experiment in particular was which strategy would be the most effective for this precise co-manipulation, and even more, how humans are able to do it, so that we could try to emulate it with robots later. The human motor behavior was measured with several motion capture, with a motion capture system that was associated with several motion capture markers on the subject, and also with muscle activity sensors, surface EMG sensors. Also, we had a measure of the times that the tube contact had contact on the tubes to quantify errors and precision while doing the task. In this human behavior study, we were able to verify that the diets were actually more effective during the conditions where both agents increased their arm stiffness, their arm muscle co-contraction, and consequently increased their arm stiffness to levels that were similar to when they were leading the task on their own. So with this information, we were able to finally propose a human-robot interaction variable impedance strategy for the robot for the same task that hopefully could be just as efficient as this human-human collaboration without pre-assigned leaders. In this other follow-up study, one of the human agents was replaced by a robot manipulator, the Franca Panda robot. For the collaboration conditions in which there was no leader, nor the robot nor the human, we proposed to vary the stiffness of the robot according now to the human partners, of course, muscle co-contraction. Unfortunately, I don't have much time to go over all of the details of this study, but you can also check it in the preprint associated with it that we just submitted. I submitted it last week, and is already available online. Later, when you get the PDF, you can search for it, or maybe print screen right now, and then later you can Google it. It's already available now as a preprint. In any case, we verified in this human-robot experiment that the conditions with a strategy without pre-assigned leaders were also more efficient for the task. This is something that we were able to propose because of the human motor behavior study. So when we think about human-robot interaction studies, that's basically why I'm advocating for more human motor behavior studies. It was only possible because of that. So human motor behavior studies basically can lead to better strategies for controlling interaction behaviors in human-robot applications. Now, time to some final considerations. And a summary, of course. With respect to our initial goals and contributions, we were able to achieve automatic ergonomics evaluations regarding kinematics and dynamics ergonomics scores using a lightweight digital human model. In addition, we also proposed methods for automatically optimizing initial movement demonstrations using single and multiple objective approaches. As we mentioned in the introduction, before being able to drive the human towards such ergonomic trajectories, human interaction behaviors should be studied. Then, in the latter part of my thesis and of this talk, we studied in this talk I showed it. We studied the motor behavior of human-human dyads during a co-manipulation to ultimately devise variable impedance profiles for a human-robot co-manipulation. With minor adaptations, the tools provided here could be integrated into one application where the robot finally drives the human towards more ergonomic whole-body trajectories. So now we arrived to the end of this talk, and I would like to thank the presence of everyone here. And now I'm very eager to discuss the topics I presented here with all of you.
Thank you very much for the interesting presentation, Valdis. I think it shows a lot of different application of digital human modeling for ergonomic evaluation, so that was really great. Just before we go to the Q&A session, I would just like to give a short overview about Anybody Technologies online resources and also the upcoming events we have scheduled. So first of all, if you want to know more about Anybody Technology, you can go and check out our website, anybodytech.com, where you can find different events and special dates, previous webcasts, and also a full publication list of studies using the Anybody modeling system. We do also have a website called anyswit.org, which is our community website for people using Anybody. Here you can find multiple online resources as our wiki page, several blog posts, and links to the repository sites. It is also here our forum is located, and you can go and ask questions and get help. I would also like to announce our presence at the Veracon event, which is going on in Scottsdale, Arizona on April 25th, 26th. And if any of you are attending this event and want to meet up with us, then please reach out and let us arrange a meeting. I would also like to point your attention to an upcoming PhD course by Aalborg University. And the course is named Musculoskeletal Modeling by Multibody Dynamics. It will be held online from May 2nd to May 6th, and the registration deadline is April 15th. The course is a beginner's course, and it can be attended by both academic and industrial institutions, and more information can be found on our website in the events section. Last but not least, if you have any questions or you just want to meet up or you're interested in a trial version of our software, then please feel free to send us an email at sales@anybodytech.com. And if you have any follow-up question regarding this webcast or any of the previous ones, then please feel free to send me an email at ki@anybodytech.com or reach out to me through LinkedIn.